We're always hearing about these incredible medical breakthroughs, right? A new drug, a new cure. But what we almost never see is the mess behind the scenes. Today, we're going to pull back that curtain and take a peek at how researchers handle all the chaos to get their results. Think about it. Every amazing clinical trial starts out with this perfect, beautiful plan on paper. It's pristine. But then you introduce people into the mix, and people are messy and unpredictable, right? They don't always follow instructions, doctors might make a mistake, some people just drop out altogether. So how in the world do you get a clear, reliable answer from all that chaos? That is the huge question we're digging into today. Okay, so before we dive into the mess, let's first set the stage. We need to understand what the ideal scenario looks like. What does a perfect medical experiment even look like on paper? All right, it's called a randomized controlled trial. You'll see it as RCT, and it is absolutely the gold standard and for a really good reason. The idea is simple. You take a big group of people, and then you randomly, like flipping a coin, assign them to get either the new treatment you're testing or the standard one. Now, in a perfect world, everyone follows the rules to the letter. And if they do, all you have to do is compare the results from the two groups, and boom, you've got a super clear, totally unbiased answer. You know if the new thing works. But, of course, we don't live in that perfect world, do we? So let's take a hypothetical study and watch just how fast that beautiful, ideal plan can completely unravel when it smacks into reality. Okay, so picture this. We've got a study testing a new airway device. Let's call it SLIPA. And they're comparing it to the standard procedure, intubation, to see which one leads to less of a sore throat after surgery. We've got 12 patients, and they're randomly and perfectly split into two groups of 6. Everything's neat, it's clean, it's organized. So far, so good, right? But this is exactly where things start to get, interesting. Because in the real world, a setup this neat almost never stays that way. In fact, it's about to get really, really messy. And here's the mess. First off, 2 of the patients who were supposed to get the new SLIPA device, they couldn't for whatever reason, so they ended up getting the standard intubation instead. Then, over in the other group, a researcher makes a mistake and accidentally gives a patient the new SLIPA device instead of the standard one. On top of that, another patient just disappears. They drop out of the study, so we have 0 data on their outcome. And to cap it all off, we find out one patient shouldn't have even been enrolled in the first place because they had diabetes. All of a sudden, our 2 perfectly clean groups are just a total scramble. You can imagine this creates a massive headache for the researchers. I mean, who do you count? And where do you count them? Do you analyze patients based on the group they were supposed to be in, or the treatment they actually got? Or do you just throw out anyone who didn't follow the plan perfectly? This, right here, is the analyst's dilemma. So how do statisticians even begin to navigate this kind of minefield? Well, it turns out there are 3 main strategies they use to try and find a clear answer in all this chaos. Okay, the first and probably the most common approach is called intention to treat, or ITT for short. And the philosophy here is super simple. Once randomized, always analyzed. It means everyone stays in the group they were originally put in for the final analysis, no matter what happened later. It doesn't matter if they took the wrong drug or dropped out. And this is really powerful because it protects that original randomization, the thing that keeps the study fair and unbiased in the first place. The second way to do it is called an as-treated analysis. And this one seems more intuitive, right? You just analyze people based on the treatment they actually got. So those patients who switched groups, you just move them over in a spreadsheet. But here's the massive problem. By doing that, you've completely destroyed the randomization. And when you do that, you open the door for all sorts of biases to creep back in, which is exactly what you were trying to avoid. And then there's the third method, per protocol analysis. You can think of this as the perfectionist's approach. You only look at the people who followed the rules perfectly, got the right treatment, finished the study, no screw-ups. Anyone who deviated even a little, they're out. This analysis doesn't tell you how the treatment works in the real world. It tells you how it works under absolutely ideal, perfect conditions. So these different methods, they aren't just, boring technical details. They actually represent a really fundamental choice. Are you trying to figure out how effective a treatment is in the messy real world, or are you trying to see how effective it is under perfect laboratory-like conditions? Let's put them side by side. Intention to treat, or ITT, answers the question, how good is the strategy of trying to give people this treatment? It's great because it keeps bias super low. The downside? It can sometimes water down the results and make the treatment look less effective than it really is. Now, per protocol, the PP analysis asks a totally different question. How well does this treatment work if someone follows the instructions perfectly? This shows you the treatment's absolute best case scenario, its maximum potential. But the results can be biased because, let's face it, people who follow rules perfectly might just be different from those who don't, in ways that could totally skew the outcome. And this difference is so important. Think about it. ITT is more conservative, it's a higher bar to clear. That's why regulators often demand to see an ITT analysis when a company is trying to prove their new drug is better than the old one. But on the flip side, the more optimistic per protocol analysis might be used when they're just trying to show a new drug is not worse or non-inferior to what's already out there. It's a strategic choice.
Okay, so we've talked about how to handle people who don't follow the rules, but what about the people who just vanish? Remember patient D who dropped out? What do you do when you just have a big empty hole in your spreadsheet where their data should be?
Well, back in the day, the solutions were pretty crude. The easiest thing to do was something called complete case analysis, which is a fancy way of saying you just delete that person's entire row of data. Gone. It's easy, sure, but you're throwing away information and losing statistical power. Another old school trick was to just plug in the average score from the rest of the group. But that's a really bad idea because it artificially squashes all the natural variation in the data and can really mess up your final results. Thankfully, today we have something way more sophisticated. It's called multiple imputation, and it's pretty brilliant. Instead of making one single bad guess for that missing value, a computer model makes multiple, really smart, educated guesses. It looks at everything else we know about that patient and creates, say, 5 or 10 plausible values for that missing spot. This gives you several complete versions of your dataset. You run your analysis on all of them, and then you combine the results. It's an incredible way to handle missing data while being totally upfront about the uncertainty involved.
Okay, so intention to treat, per protocol, multiple imputation. I know it's a lot of statistical jargon, but why should you actually care about any of this when you see a news story about some amazing new medical breakthrough?
Here's why. Because the most reliable, trustworthy studies aren't the ones that pretend everything went perfectly. They're the ones that are totally upfront and honest about the mess. So next time you're looking at a study, see if you can find the section where they describe how they analyze the data. Did they use intention to treat? Did they tell you exactly how they handled people who dropped out or broke the rules? That kind of transparency, that is the hallmark of a high-quality, reliable study. And here's the ultimate confidence boost. The source material for this explainer says it perfectly. When both the real-world intention to treat analysis and the ideal-world per protocol analysis lead to basically the same conclusion, well, that's when your confidence in the results should just skyrocket. It tells you that the effect they found is real and robust. It's not just some fluke based on how they decided to crunch the numbers. So I'm going to leave you with this one thought. The next time you see a big headline celebrating some new medical breakthrough, don't just ask yourself, does it work? I want you to go one level deeper. Ask the much more powerful question, yeah, but how did they count?